So at the beginning of video 1, we rearranged the equation 8x cubed plus 11x squared plus x minus 1 equals 0 in 3 different ways. And we used this central rearrangement to create an iterative formula. And we managed to find 2 roots of our equation, but we were unable to find the third root. And we're now going to have a look at this third rearrangement and see if we can use that to find the root that we were unable to find previously. So a quick reminder that we had 3 roots that we can see that they are here in the intervals -2, -1, -1, 0 and 0, 1. And they are the roots of this equation which we are solving, and we were able to find the roots in -1, 0 and 0, 1 intervals, but we were unable to find the root in the -2, -1 interval using the rearrangement that we had before and using the iterative formula that we used before. So we're now going to use the rearrangement x equals the cube root of 1 minus x minus 11x squared all over 8 to find a root of our equation, and hopefully the root in the interval -2, -1. So I'm going to introduce a little bit more formal notation than I did in video 2, in that I'm going to introduce g of x, and g of x is the rearranged expression on the right hand side. As you know, when we have rearranged the equation at the top, we're then going to draw 2 graphs, y equals x and y equals g of x, which is going to be our rearranged right hand side. And so g of x in this particular case is the cube root of 1 minus x minus 11x squared all over 8. Our general iterative formula here is using this rearrangement that each successive value of x is generated using the previous one, and the iterative formula is the cube root of 1 minus xn minus 11 xn squared all over 8, and that generates xn plus 1. So we're going to look at these 2 graphs. We discussed before the importance of the gradient of the curve y equals g of x, and that gradient needs to be between -1 and 1 if the fixed point iteration is going to work. In the previous rearrangement, the previous iterative formula we used, it didn't work in the interval -2, -1. We're trying to find the root here, which is the intersection of these 2 graphs, and you can see here that the blue curve, which is y equals g of x, the gradient is below the y equals x line, and the y equals x obviously has a gradient of 1, so we can say here that the gradient of the curve is between -1 and 1, i.e. g dashed of x is between those 2 values. And so it should work that we can use this iterative formula. And indeed you can see on the spreadsheet, so this is following exactly the same format that we used in the previous videos, that we have an x0 value, and the x0 value is -2, that is substituted into our iterative formula to generate here the value x1, and that is then transferred across. This is actually gx of n, because we are using the graph y equals g of x, and so just being a little bit more formal in our notation. So if we look at the spreadsheet that we've got here, we can see that our values of xn are getting closer and closer together, that they are heading at the bottom here towards -1.18 to 3 significant figures. If we wanted to go a little bit more accurately to 5 significant figures, we need to extend these spreadsheets which I've done here. And so I'd like you to look at these spreadsheets and find this root to 5 significant figures. So you can see that after 32 iterations, you have got a root of negative 1.1791 to 5 significant figures. I have substituted the error bounds back into our original expression that was in our equation, and we have got a negative and a positive value for f of x, which shows that our graph has cut the x-axis in between, and so it verifies our root. Again, I've carried the spreadsheet on a little bit just to check that this value of x is not heading down far enough to go down to negative 1.1790, but it is slowing down a lot, and you can see that it actually is heading to negative 1.1791, and that's confirmed by our error bounds. So let's have a look at what's happening graphically. Again, we are going to consider our x0, which this time is negative 2. And we know that we are going to substitute that into our iterative formula, which means that we are going to draw a line to our blue curve. And at that point, we have the coordinates here. The x coordinate is going to be x0, and the y coordinate, I'm now going to call it g of x0. It's still a y coordinate, but because I've now said that the graph here is y equals g of x, and g of x is our cubed root of 1 minus x minus 11x squared all over 8, and it's being a little bit more formal. We're then going to transfer that value across to our y equals x, and at this point here we then have a y value still of g of x0, but our x value is now the same, and so our generated new value of x, our x1, is generated using our g of x formula or our iterative formula. So this is now x1, g of x0. And we're going to follow that. Again, you can see it's going to be a staircase pattern this time, and it's going to head up towards this point of intersection and our root. So I've drawn in the first few stages of the staircase diagram, and you can see that it's converging nicely onto that root. So what happens at the other two roots? Are we able to find them using this particular iterative formula that I've got? So this root and this root are, the other two roots are where the two graphs intersect, and you can see that the gradient of the blue curve is too steep. It is at this particular root here, then we have that g dashed of x is going to be greater than 1. It's steeper than the y equals x line, it's cutting right across it, and at this root here, this point, the value of g dashed of x is going to be less than negative 1. It's coming down at quite a steep negative angle. So let's just have a look and see what would happen with this particular iterative formula if we were to start with a value of x0 at 0. And we'll just graphically have a look at what would happen here. As you know, we need to go to our curve, so we would go straight up to our curve. That would then generate a y coordinate, a g of x0, and we would then transfer that to our x value by moving across horizontally to our y equals x line. And then we would want to move to our curve again so that we could then substitute that new x value in to generate the new value of x, and we would then move down to this point here and then to move horizontally across to our y equals x line. And what's happened is we've actually gone right back across towards the route that we've already found. And if we were then to continue our iterative process, you can see quite clearly that when we go between the curve and the straight line, we're actually going to head down towards the route that we've just found with a start value of -2. And so we haven't been able to find either of the roots in the interval -1, 0 or 0, 1, even though we've started at 0, which is in between those two roots. So this particular iterative formula has not found those two roots, but it did find the first root, the one in the interval -2, -1, which we were unable to find before. So let's finally just consider our final third rearrangement that we did at the beginning of video 1. We rearranged our equation to get x equals 1 minus 8x cubed minus 11x squared, and that would generate the iterative formula here. Xn plus 1 is 1 minus 8xn cubed minus 11xn squared. And without doing the Excel spreadsheets, I'm just going to look at the graphs. So we have our two graphs. We have y equals x, our straight line, and we have our y equals g of x, where g of x is our 1 minus 8x cubed minus 11x squared. And we're going to consider the gradient of this curve at the points of intersection with the line y equals x, which is where our roots lie. So we have these three roots, and we're going to consider whether or not we think this particular rearrangement would work for any of these roots. You can see quite clearly that at the root in the interval -2, -1, the gradient of the curve g dashed of x is going to be less than -1. It's coming in very steeply and cutting down on the y equals x line. At the central root, then we have that g dashed of x is going to be greater than 1 because it is cutting up over the y equals x line. And at the third root, we have got that g dashed of x is less than -1. So actually, this particular rearrangement doesn't find any of the roots. It wouldn't find any of the roots. Let's consider what would happen if we had a start value of 0. So if x0 is 0, and we're going to start, as we always do, with going up to find our curve. That generates our new x value, that generates x1, and we would then transfer that y value to our new x value by going across to y equals x, and you can already see what's happening, which is that this is then going to go all the way down, and although it doesn't meet on our graph, it is going to meet somewhere on a very, very low value of y, which would then give us a very large negative value of x that would then transfer across, and it looks as if it's just going to head right off to oscillate between negative and positive infinity, because that value would then go across to find y equals x, which would then go up. So if we imagine that it's going to somewhere down at the bottom, then find the curve y equals g of x, and then try and find the line y equals x. We're going right outside the remits of this graph. It's not going to converge on any of the roots, and it doesn't if we have any of the start values -2, -1, 0 or 1. They're not going to work with this particular rearrangement. So we have used these three iterative formulae to try to solve the equation at the top of the page with relative degrees of success with each one.